Hey everybody, Dr. Phil here. So this first video is a little bit on a background to statistics. What is statistics? Why is it important? So the first thing we're going to talk about is why should you study statistics? So I'm sure most of you are aware of this. We live in what we could call the information age, right? Like data is being collected by companies, by individuals, through social media, for example, at a rate that the world has never seen. It's somewhat unprecedented. Um, the only way that we can really make any sense of just having so much data coming in now is we need to have an understanding of statistics, so we can kind of understand how do we make all this data coming in useful? Because otherwise, what's the point collecting it, right? Um, we can also say that statistics is used to make valid comparisons and to predict the outcomes of decisions. Now, when it says predict, I want to be clear about that. That doesn't mean that we're saying that this will definitely happen. There's a distinction we make in statistics and in the wider world of correlation versus causality. To say something causes something else is a pretty bold statement in any field, including statistics. So most times we'll say that variable X has say a correlation with variable Y, for example, or variable A has a correlation with B. We won't generally say that something is caused by something else. We try to usually stay away from that language. Um, so whatever degree you're here to get, statistics is going to be useful to you. It's going to help you. All right. So what is the formal definition of statistics? And again, everybody has a slightly different definition of this, it seems. The science of collecting, organizing, presenting, analyzing, and interpreting data to assist in making more effective decisions. That's a pretty good definition. So as an example, the inflation rate for the calendar year was 5.4%. So that is a statistic, right? That is a number that is meaningful in the context of something else. So what can we do with that 5.4%? Well, we can compare it to the previous year to say, okay, is inflation, better or worse than it's been in last year, or say the last 2 years or 5 years? Um, is there a trend of increasing or decreasing inflation? That's certainly good to know if something you're like, let's say you're the Fed, right? And you're the folks that try to figure out, do we need to increase or decrease interest rates under that quantitative easing umbrella? Is there a relationship between interest rates and government bonds? So these are all things that, understanding the inflation rate, understanding in this case, the implication, the repercussion that would have on interest rates. Um, this is a good use of statistics. So we really have two types of statistics. We have what we call descriptive, and then what we call inferential. So let's talk about maybe the easier one first. So descriptive statistics can be used to organize data into a meaningful form. Um, so you can summarize data and provide information that's easy to understand. So we can think of descriptive statistics of we want to organize, we want to summarize, and we want to present it in an informative way. So, as an example, there are a total of 46,837 miles of interstate highways in the US. So that is in and of itself a statistic. The interstate system represents 1%, there you go, there's another one, of the nation's roads, but carries more than 20%, there's another statistic, of the traffic. Texas has the most interstate highways, and as it turns out, Alaska does not have any. So you can see a little kind of practical use here of descriptive statistics. Now, what about inferential statistics? So inferential statistics can be used to estimate properties of a population. So it helps you make decisions based on a limited set of data. Now, when they say limited set of data, think about like sample versus population. I'm sure those are all terms you've heard before. You may have taken a stats class in the past, or perhaps in high school. And the idea is, well, we can't. It's too expensive. It's too time consuming to get the whole population. So what we do is we take a sample, what should be a representative sample, right, a non-biased sample, a randomized sample, and then we try to make inferences. Think of an inference as like an educated guess, right? So if somebody says, I'm inferring something, it means they're kind of really just guessing it based on other things that they've seen. All right, so inferential statistics, the methods used to estimate a property of a population on the basis of a sample, as we were just saying. So as an example, by way of example, in 2021, A vaccination for COVID-19 was freely available. To determine who did not get the vaccine, random samples of people were selected and surveyed. And then what is the proportion of people that did not get the vaccine? So think about, you're going to get a sample, right? They didn't survey the whole population, right? They just took a sample. So long as, and this is really important, so long as the sample is representative of the population, then you can make inferences about the population, like your quote unquote educated guesses about the population based on what you learned from the sample. So we think of the population as it says, the entire set of individuals or objects of interest, or the measurements obtained from all individuals or objects of interest. Usually, as I said, the population is usually way too many people, too many data points to collect. Hence why we do it. The sample is cheaper, it's quicker, and it's more realistic in terms of, how long are you going to take to publish the study if you do the whole population? Probably decades. So the sample is a portion or part of the population of interest. So as you see here, right, they've got all these vehicles, and what they've done is they've said, okay, let's just randomly pick some, and the randomization here looks pretty good. I know they don't use the word randomization here, but if you look at the colors they picked, like, they didn't just pick all like green or yellow or blue. They picked a range of different colors. So that would lead us to probably believe that the sample was randomized. Okay, two types of variables. Very basically, there are two types. So we have what we call qualitative and what we call quantitative. Before I get into their definition, let me just say this. Qualitative, just think of anything that's not numbers. Quantitative, just think of anything that is numbers, and that's pretty much it. So qualitative variable is defined as an object or individual that's observed and recorded as a, there you go, non-numeric characteristic or attribute. So examples would be gender, state of birth, and eye color. Of course, they're all non-numeric, right? Now let's talk about quantitative variables. A quantitative variable is a variable that is reported numerically. So, for example, balance in your checking account, right? $500, that's a number. The life of a car battery, say 3 years, three's a number. The number of people employed by a company, they've got 300 people working there. Again, it's a number. So, if you want to express this graphically, we can kind of break it down like this, right? We've got our qualitative, again, non-numerical on the left. So if you look at the examples here, brand of PC, marital status, hair color, again, no numbers there, right? And then on the quantitative side, on the numerical side, we have what we call discrete, and then what we call continuous. I'll explain those in a second. So discrete, if you look at the children in a family, strokes on a golf hole, TV sets owned, and then compare it to continuous, which says amount of income, tax paid, weight of a student, yearly rainfall in Tampa, Florida. So you might be like, okay, well, they're both quantitative. I'm not sure I see the difference. So think of discrete as it's moving up in increments. So like number of children in a family is like 0, 1, 2, 3, right? 4, so on and so on and so forth. Strokes on a golf hole, right? So 1, 2, 3, 4, so on and so forth. You can't have like 4.1 children in a family, right? You go from 4 to 5. So that's that incremental step up, if you will. You can't have like 4.273 children, right? You either got 1, you got 2, you got 3, you got 4, you got 5. Same with TV sets owned, right? You've got 0, you got 1, you've got 2, you've got 3. You can't have 1.217 TV sets, right? So that's where the continuous comes in. So the continuous could be really any kind of, typically any number at all within a range. So like amount of income tax paid, you could have paid $1,200 and I don't know $17.52, and I could have paid $1,217.53, and then one of you else could have paid 1,217.54, so on and so forth. So that's the difference between discrete and continuous. All right, so as we said, this is just there. I just wanted to kind of set this up for you. So quantitative variables can be discrete or continuous. Discrete variables are typically the result of counting. So the values have gaps between the values. So think about, as their example, the number of bedrooms in a house, right? 1, 2, 3, 4. You don't have like 1.017 or 2. I don't know, 574 bedrooms. It's just going up in those by those gaps, if you will. The number of students in a statistics course could be 1, it could be 10, it could be, but it wouldn't be like 1.7, right? Or 1.5172. It would always go up by, incrementally. Now, continuous variables are usually the result of measuring something. Now, they can assume any value within a specific range. So examples could be the duration of flights from Orlando to San Diego, 5.25 hours, or grade point average, 3.258. So like your grade point average doesn't have to be like, 1.0, and then it goes right up to 2.0, and then, 3.0, and then 4.0, right? It can be anywhere between really 0 up to 4.0. It can assume any number. Okay, so there are really four levels of measurements. Okay, so we have nominal, we have ordinal, we have interval, and we have a ratio. So let's just take a minute and talk about these. So if nominal, then the data may only be classified. So for example, jersey numbers of football players, or like the make of a car, right? So think about like nominal as name. So like the make of a car, it's a Honda, it's a Toyota, so on and so forth, a Nissan. Ordinal speaks to how the data are ranked. So your ranking class. So this is where it's really still names like nominal, but it's now there's a ranking order. So like a college would be a good example, right? You are a freshman, you are a sophomore, you are a junior, you are a senior. Or team standings in the Southeastern Conference, that's another one that you could use too. Interval, meaningful difference between the values. So things like temperature, right? If it's 20 degrees versus 30 degrees Fahrenheit or Celsius, it doesn't matter. That represents a meaningful difference. Dress size also represents, of course, small, large, extra large, medium, whatever else. They represent meaningful differences. And then finally, ratio, which is maybe like the more like, or the most like complicated, if you will. Meaningful 0 point and ratio between values. So, for example, like profit, if you have zero profit in a company, basically means you're breaking even, then that is still a meaningful number. Okay, fuel efficiency and distance to class could also be examples. So let's just run through their definitions real quick. So nominal, this is the lowest level of measurement. So the nominal level of measurement is data recorded at the nominal level. It is represented as labels or names. You heard me say names earlier. They don't really have any order. It's not like one name is better than the other. They can only be classified and counted. So examples could be classifying M&M candies by color. Doesn't mean that, red is better than green or blue is better than yellow, so on and so forth. Or identifying students at a football game by gender could also be an example. The next higher level of measurement is the ordinal level. So the ordinal level, think about ordinal as in order, there's an order to things. Data recorded at the ordinal level of measurements is based on a relative ranking or rating of items based on a defined attribute or qualitative variable. So variables based on this level of measurement are only ranked and counted. So for example, the list of top 10 states for best business climate or student ratings of professors. So again, professors would get a rank. Top 10 states for business, like number one would be the best one, number two. So this is where this ranking comes in. Okay, the next higher level of measurement is the interval level. This data has all the characteristics of ordinal level data, but the difference between the values now become meaningful. So because they're meaningful, there's no natural 0 point. So the interval level of measurement for data recorded at the interval level of measurement, the interval distance between values is meaningful, as we said. The interval level of measurement is based on a scale with a known unit of measurement. So examples could be the Fahrenheit temperature scale or dress sizes that we discussed earlier, right? If it's 10 degrees Fahrenheit or it's gone up to 15 or it's 20 or it's 50, 70, whatever it may be, these all represent meaningful. But you think about there is also no natural 0 point in that sense. Now, the highest level of measurement is what we call the ratio level. So this is the most, none of these are complicated, right? But this is like the most complicated, if you will, like air quote that. The data has all the characteristics of the interval scale, and ratios between numbers are meaningful. The 0 point represents the absence of a characteristic. Okay, so data recorded at the ratio level of measurement are based on a scale with a known unit of measurement and a meaningful interpretation of 0 on the scale. So for example, wages. So if you have 0 wages, right, that represents the absence of wages, right? If you have, let's say, 0 in stock capital gains, then that represents an absence of a gain, right? So on and so forth. But think about why the 0 point represents the absence of the characteristic. Like, if the temperature is 0, it doesn't mean that there's no temperature, right? This is where this actually represents the absence of a characteristic when you hit 0. Okay, that's all for this video. I will see you in a future video. Thanks.